All right, so now we're going to talk about joint densities. And we've already described random variables. This is when we were learning about probabilities in terms of a population data set, right? So you imagine there's a bunch of people. We have this data set where these different variables are measured for each person. And we know that we can define probability of multiple things happening at the same time, the same way that we define probability of a single thing, like the probability that somebody's wearing a hat is just the number of people in the population who have hats over the total number of people in the population. We can define the probability of a joint event, like that somebody's a pink person and they're wearing a hat, as just the total number of pink people wearing a hat over the total number of people in the population. So that's the same. And what we've just been doing is saying, okay, well, how can we abstract away this population data set so we don't have to deal with it? And even though, conceptually it's nice to imagine it that way, but when we start doing stuff later, we'll see densities are nicer to work with. So how can we get rid of that? For a single random variable, we were just talking about that. Now we can ask the same question when we have multiple random variables. How do we define what's called a joint density or a joint distribution? So that's the purpose of this section here. So let's just start out with discrete random variables. So here in this little example, I have a population data set that has two random variables, chromosomal sex and age, okay? And both of these are discrete in that they only take a finite number of values. So age in this example, let's say these are all preschoolers, so they're between 1 and 5 years old. And sex is, for the purposes of this example, again, binary, so just F or M. And the way that I can calculate the density from this population data set is the same as I did before. So this is the code. If I had this population data set, I would just be counting each unique combination here of age and sex. So the difference from before is that when I was getting the density for a single random variable, I was just counting each unique value of age. Now I'm counting each unique combination of age and sex. And then this line here just takes that count and divides it by the total number of people in the population. So what we see here is that 10% of people in this population are 2-year-old males, okay? And 15% are 3-year-old males, and so on and so forth. So that's all that this is, and this is our density function. So you can think of it as a table. I think we'll talk about this in a second again, but you can think of it as a table where for each age and sex you have a value of the function, or you can think of it as a function where if I give you the age and I give you the sex, you put it into this function and it returns this value in the table. It's equivalent. It's the same thing. So so you can visualize such a function as well, which is, if you're thinking about functions, you're from pre-calculus and whatnot, you're usually thinking about graphs. So we can graph this if we wanted to. So on the x-axis, we'll put age, and on the y-axis, we will put the value of the function, which in this case is the probability of being that age. However, now since we have two random variables, we actually have to graph two kind of independent variables at the same time, and then this thing is like our dependent variable. So here we have age on the x-axis. We could have another axis down here and then put the output on the z-axis. I'm just going to break it up into two plots. So I'm going to say for sex equals F, age is on the x-axis, this is the probabilities. And for sex equals M, age is on the x-axis, these are the probabilities. So I've broken it up into two graphs, just showing you can still plot it. Or if you want to see it on the same graph, you could do it like this, where I have sex as an axis, I have age as an axis, and I'm kind of plotting the values of the function here. It's not a curve because these are discrete random variables. And another way we could visualize this is perhaps as a heat map. So this picture, I'm kind of looking from the top down onto this graph. Imagine kind of standing on top of this. And these high values here, the higher values are going to be brighter, and the lower values are going to be more dim. So that's what we're seeing here. So this kind of dim value right here corresponds to this right here. And this very high value is this one. So I'm just looking down onto this graph. Again, these are this works because we're looking at densities that are defined on two dimensions, and then we have the density here. If you had 3 random variables, you could still construct a table like this by taking the unique combination of 3 or 4 or 5 or whatever, all the possible unique combinations, and then assigning the density by counting things in the population data set. This still works, but you can't, it's harder to imagine what that would look like in terms of a graph. You would have to have a lot of different facets, and certainly something like this you could not do. But if you had enough facets, you could plot such a thing. But it's still a function in the sense that if you give me the values of the random variables, I can tell you what the probability is of finding that combination in the population. So that is the joint density, or a joint probability density function, PDF. And like the kinds of densities that we were looking at before, these things are useful because you can calculate probabilities from them. So for example, let's say that I want to know here the probability that x is greater than or equal to 2 and y is 0. What I have to do is just add up the values of the density function where, for all inputs where x is greater than or equal to 2 and y is set to 0. Why does that make sense? It's the same as before. So if you think of the population data set, and so here this is a very, very small, artificially small population data set, right? There's only 6 rows. If I were to calculate this probability, I just need to count how many times this happens in my population, right? And then divide by the total number in my population. So if I check here, okay, here x is greater than or equal to 2 and y is 0. So that counts as 1. This one is, here's another instance where that happens, that's 2. And here's the last one, so it's 3. So there's 3 out of 6 times, right, where this thing happens. So that total probability is 1/2. So what if I look at the density function instead? So here I've just tabulated how many times each of these combinations occurs. So for example, this 1 and 0 combination corresponds to this row here. That occurs 1 time. But there's some rows that occur twice, right? So here we have 2 and 0. That happens twice because this row is 2, 0 and this row is 2, 0. So I have 2 tabulated there. There's some rows that occur never. So there's no instance of 4, 0. So that gets a 0 out of 6. So if I want to calculate the probability that x is greater than or equal to 2 and y is 0, I could just count the rows in the population data set. I could also just sum up the values corresponding to the allowed rows in this condition, which are any number greater than 2 here, greater than or equal to 2 here, and a 0 here. So if I just look at the rows where that happens over here, I have 2 plus 1 equals 3, 3, 6, right? Why is that the same? Because this 2 just comes from this row and this row. So again, it's just counting. I'm just counting first by grouping and then summing the counts, or I'm counting directly in the population data. This is just kind of like a pre-grouped, the density is just kind of like a pre-grouped version of the population data with things counted up and normalized by the total number in the population. All right. So this is showing you the same thing. So let's say if we were representing our density or visualizing our density in terms of a heat map. If you're asking about the probability that, in this case, age is greater than 3 and sex is M, what is that? What you need to do is you need to find the kind of conditions on X and Y that you're asking about, and then add up the value of the density for those conditions. So in this visualization, we're asking about sex equals M, so it's this kind of column here, and then age greater than 3, so 4 or 5. So I've outlined the kind of like boxes, in this case the rows of the density, but in this visualization it's like the cells where that is happening. And then what I need to do is add up the numbers in those 2 cells. So the answer I should get is about 0.2. And you can see that you get the same answer whether you take the PDF, you just get out those 2 values by filtering those rows. So I'm getting rid of all these other rows. I'm just keeping these ones effectively. And then I'm adding those values, sorry. I get the same answer as if I were to take the population, filter the entire population, and then just count how many people I have left divided by the total number in that population. So it's adding this formula here where you're adding up values of the PDF. It's just a convenient way of kind of counting, right? So let's do a little problem here. Again, I encourage you to actually pause and try this yourself. Check your understanding, feel free to rewind and watch things if you have to again. The question here is that you are interested in education levels, and you have mothers and their first child who is, we're presuming, over 30 years old at this point in the US population. So X is going to be the mother's education, and Y is going to be this child's education. And you have a colleague who hypothesizes that the joint density for these variables looks something like this. So I've given it to you here as a kind of two-way table, but remember you could also look at this as a table with like we were looking at it here, where you have, this was mother's education, this is the child's education, and this would be the density. This is just another way of organizing those data. Once you have more than two random variables, you can't do this unless you could have like a 3D table, like a cube, but it gets ugly. But in this case, I'm giving it to you like this because it's nice. And I have a couple of questions here. So one is that, okay, so this is the density that your colleague postulates. And the first one is, does this seem plausible to you? So kind of considering, what you know about education, patterns of education in families in the United States, do these numbers agree with your intuition? Sorry. And then the second question, so that's qualitative, just to kind of check your understanding of what do these numbers mean and do they agree with reality? And then the second question is that given that let's say that it's right, okay? If this is right, then what's the chance that a mother actually has a final higher education level than their first child? And then the third is just to kind of practice our notation and writing this down in probability notation the way that a statistician would understand. So, okay, first question, is this plausible? Well, let's look. So first, right off the bat, maybe what we should do is say, what are the most likely outcomes here, right? So we have these numbers, 16%, 18%, 12%. These numbers are much smaller, like 9%, 4.5%, 1%. So does it make sense that most people, most kind of mother-child pairs are relatively low education? In the US, I think something like 30, 40% of people have high school education or less. So this kind of tracks. Again, I don't know too much about this. I'm not an expert, but if somebody showed this to me, I would think that that aspect of it is kind of reasonable. The other thing that you might notice is that if for a mother who has no high school education compared to one that has some high school education, the child is more likely to have more education when the mother is more educated. So I get maybe that's easier to see here. So comparing like college to no high school. For no high school, we have most of the kids are either no high school or just high school, and then there's a big drop off, right? So like the ratio between grad school and high school is like 3-1 among the no high school mothers. But if you have a mother who's gone to college, you're about equally likely to not graduate high school as you are to go to grad school. So you have a much higher chance, relatively speaking, of getting grad school if your parent if your mother has gone to college. So again, not an expert in education and patterns of education in families, but based on what little I know, that kind of seems to track for me. I think that makes sense that if your parent is educated, that you'll have a higher chance of going on in higher education. So for question one, I think, yeah, it's plausible. And of course, the idea is there's not a right answer to that question. It's for you to start kind of connecting the definitions of these things to what is happening in the real world and always be kind of fact checking yourself like that. So that's question one. Question two, given this distribution, what's the chance that a mother has a higher final education level than their first child? So this is an interesting question. It's a little bit different than what we were seeing before, because before we were asking about, okay, assuming that let's say the mother's education is 1, we want to know the probability of mother's education equals 1 and child's education is greater than 2 or something like that. Like if you go to the previous slides, we were asking about probabilities like that. But here, we're relating the mother's education to the child's education. So in the previous example, like let's say if we were saying mother's education is no high school and child's education, so equal 1, and child's education is greater than or equal to 3, we might be referring to these boxes here, right? So we would add up the value of the density in these two boxes, and the answer would be 18%, right? If that were the question, but that's not the question, right? The question is, what's the chance that the mother has a higher final education level than their first child? So how do we do that? Well, let's just look at each of these cells and just highlight the ones where that's the case. So here, for example, if mother's education is for this cell, mother's education is no high school and child's education is also no high school. So no high school is not higher than no high school. They're the same. So that one does not qualify, right? Similarly here, the mother is 1 for education and the child is 2. So mother's education is less than the child. So that does not qualify. And if you do that exercise, you'll see kind of all this stuff does not qualify, but this stuff does down here. And so the cells that you'll end up with are these ones. This one counts, this one counts, and this one counts. So it's this kind of region in here. And so all we need to do is add up. It's the same. It's just now we're not adding up the numbers in a kind of a rectangle. We're just adding up the numbers in some other shape, but who cares? That's fine. We can still add. So the total here will be 10, 12, 15, 16 and a half, and 17 and a half. So that totals to 17.5%. And that's the answer there. And then the next question, lastly, is write this in probability notation. So again, let's go back to the kind of thing that we were doing in the lecture portion. So this thing here, if we added up those numbers, that would be the probability that what do we have? X equals 1 and Y is greater than or equal to 3, right? I'm sorry, that's kind of ugly there, but that's what that, you know what, let's write it up here. Here. Okay. Or if you want to think about it like the region is just this kind of like event here, and then the probability is what you get when you add up those two numbers, right? The equivalent down here, how would you write that in terms of this kind of notation? It's not going to be x equals 1 and y equals 3. It's some relationship between x and y. And so if we were to say, what is it that we're selecting for here? It's all the cases where x is greater than y. So here what we have is x greater than y. So that's what this kind of, all these cells represent. And then if we want the probability of that, that's what we get when we add up all the numbers within those cells corresponding to the values of the density. All right. So that's a bit about joint densities for discrete random variables. Like we did with the kind of univariate densities, we can also talk about joint densities for continuous random variables. And it's a little bit different, a little bit more subtle, but all of the intuition is the same. So for a continuous random variable, you can think of this as like a 2D histogram where for any kind of region in the XY space, if you count how high this thing is, that's kind of like the total count of people in that area. So what I'm showing you is like the equivalent of this plot here. So this is for the discrete density, where x and y only take particular values like 5f or 4m, right? There's no values in here. There's no, category like that's like halfway between f and m, at least in this stupid example where age is recorded as like 4.25. That's just not a value that's ever exists in this population. Okay, might exist in a different population, but not in this one. So I'm showing you here the equivalent of that plot. For a continuous random variable, you have a value of the density for every possible value of x and y. But, like, you know, for x equals pi, right? There's a value of the density. And you can also plot, again, for a 2D density, you can have this kind of 3D visualization. You can also have the heat map visualization where, again, you're looking kind of from the top down. And here, what you're seeing is that the hot or pink areas are the regions of high density. And another way to imagine this is like, if you have your population and you make everyone go stand, like imagine you have your whole population and you make them go outside in like a big quad or something like that. And on the sides of the quad, you'll say, like, for example, this is like, well, I guess these are from negative to positive, whatever. Let's say this is like age, right? And this is height, right? And you have people stand at the coordinate that corresponds to their age and height, okay? And then you take a picture from the top down. These pink areas are like where people are crowding together. There's like a ton of people standing in here, and there's a handful of people standing in here, and then these gray areas are where it's very sparsely populated. There's not a lot of people there, right? So that's kind of what we're looking at. And just like in the discrete case, the probability of an event can be given by adding up values of the density. The difference here is that since the density function takes continuous values over, in this case, x and y, we can't add up an infinite number of values, and so the equivalent of that sum is this integral. Again, if you're not familiar with calculus, don't worry about this. It's totally fine. The intuition is the same. You're still kind of counting in a population data set. So it's now the area under this curve, or in this case, the volume of this region here corresponds to the probability that somebody is standing kind of at this point, any of these points in this like square within the quad, right?